This screencast is on ionic bonding, or bonding that occurs between a metal and a nonmetal. An ionic compound is made of positive and negatively charged ions that are combined so that the numbers of positive and negative charges are equal. So for example, if we have a barium ion, which is Ba plus 2, combining with a chloride ion, which is Cl minus 1, what happens is that the electrons from the barium are going to kind of be broken off and given to the chlorine. So there's an attraction, there's a bond there. But in order to make it balance out, we're going to need 2 chlorines because the barium has a +2 charge and the chlorine has a -1 charge. Our goal is to end up with a total charge of 0, right? We want our compound to be neutral. It shouldn't have any charge. So we need to add a second chloride to balance that out. So when we do that, we end up with the formula of BaCl2 because we have 1 barium atom and 2 chloride atoms. Most ionic compounds are going to exist as crystalline solids. That's just a 3-dimensional shape where the positive and negative ions are attracted to each other. So again, keeping in mind magnets where opposites attract, you're going to have the positive end attracted to the negative end of another unit. So the chemical formula of an ionic compound represents not molecules like we're used to saying, but formula units. So a lot of times you'll hear people say we have a molecule of barium chloride. That's not technically accurate. We have a formula unit of barium chloride. So the terms don't exactly mean the same thing, although we understand that they're used interchangeably oftentimes. So again, in ionic versus covalent bonding, in ionic bonding, we have 2 atoms combining where electrons are transferred. So here in this graphic, atom A is going to have a positive charge and atom B will have a negative charge. So when we look at the formula unit here, we can see where the positive and negative charges are kind of grouped together. In contrast, in covalent bonding, the electrons are shared between the 2 atoms, okay, to make a molecule. So for an example of a formation of an ionic compound, here we have a sodium atom, and you can see it has 1 valence electron, and we have a chlorine atom that's going to have 7 valence electrons. And so our metal, which is sodium, wants to get rid of its 1 electron, and when it does that, it's going to form a cation, and our chlorine wants to gain 1 electron to form an anion. So this 1 electron from sodium is going to end up being added into this 1 atom of chlorine, and that's going to give both atoms 8 electrons in their outer shell. And remember, that's our octet rule. And the reason that we want to obey the octet rule is for stability. So ions are formed so that compounds elements can come together to form a compound, and that's to obey the octet rule and to give the atom more stability because they want to be like noble gases, which are stable. So here are 2 examples of the crystal lattices. Here you can see where we have cesium chloride. There's an atom of cesium here in the center, and it's surrounded by chloride ions. Over here on the right, we have a sodium chloride. So we have the green are the chlorides and the reds are the sodiums. So you can see here where we have a negative chloride attached to a positive sodium attached to a negative chloride. So they're alternating, right, which is a positive charge and which is a negative charge. And so this is what we mean by a crystal lattice. So different combinations of elements will form different shapes. You can see how the sodium chloride shape does not exactly match the cesium chloride shape, but they still form that 3-dimensional pattern that is consistent, and that's what a crystal lattice is. So ions minimize their potential energy by combining in this orderly 3-dimensional arrangement known as the crystal lattice. So we have attractive forces between oppositely charged ions and repulsive forces between like-charged ions. So in the crystal lattice, what happens is we have our positive and negative charges lining up so that it maximizes the attractive forces and it minimizes the repulsive forces. So we want them lined up like oppositely charged, instead of having two negatives beside each other or two positives beside each other, which would cause too much repelling. So that's what creates that crystal lattice. The combined attractive and repulsive forces within the crystal lattice determine the distance between the ions. It also determines the pattern of the ions arrangement in the crystal. So like in the previous slide where we saw this cesium chloride did not look exactly like the sodium chloride, that's because that's maximizing the distance between the ions and the pattern arrangement based on positive and negative charges of the ions. Please make sure you write complete notes, and if you have any questions, ask Mrs. Benke in class.